In 2019, Google claimed it was the first to demonstrate a quantum computer performing a calculation beyond the abilities of today's most powerful supercomputers. But most of the time, creating a quantum algorithm that stands a chance at beating a classical computer is an accidental process, Purdue University scientists say. To bring more guidance to this process and make it less arbitrary, these scientists developed a new theory that may eventually lead to more systematic design of quantum algorithms. The new theory, described in a paper published in the journal Advanced Quantum Technologies, is the first known attempt to determine which quantum states can be created and processed with an acceptable number of quantum gates to outperform a classical algorithm. Physicists refer to this concept of having the right number of gates to control each state as complexity. Since the complexity of a quantum algorithm is closely related to the complexity of quantum states involved in the algorithm, the theory could therefore bring order to the search for quantum. An algorithm is a sequence of steps to perform a calculation. The algorithm is usually implemented on a circuit. In classical computers, circuits have gates that switch bits to either a 0 or 1 state. A quantum computer instead relies on computational units called qubits that store 0 and 1 states simultaneously in superposition, allowing more information to be processed. In classical computers, the number of gates in circuits increases exponentially with respect to the size of the problem of interest. This exponential model grows so astonishingly fast that it becomes physically impossible to handle for even a moderately sized problem of interest. For example, even a small protein molecule may contain hundreds of electrons. If each electron can only take 2 forms, then to simulate 300 electrons would require 2,300 classical states, which is more than the number of all the atoms in the universe, said Saber Kais, a professor in Purdue's Department of Chemistry and member of the Purdue Quantum Science and Engineering I. Polynomial means that there would be drastically fewer steps gates needed to process the same amount of information, making a quantum algorithm superior to a classical algorithm. Researchers so far haven't had a good way to identify which quantum states could satisfy this condition of polynomial complexity. They also showed that these states may share a coefficient feature that could be used to better identify them when designing a quantum algorithm. This work is supported by the U.S. Department of Energy Office of Basic Energy Sciences under Award No. DO-SC00-19215. The Purdue Quantum Science and Engineering Institute is part of Purdue's Discovery Park. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you new tech videos. Thank you.